Question 4. This question has two electric dipole, one with 0.2 nanocoulombs sitting on the x-axis, and the other one has 5 nanocoulombs sitting on the y-axis. Then you're asked to find the electric field at a vector position of 0, 0, 5 millimeter. And then you have to evaluate the force if a point charge of -2 nanocoulombs is put onto that position or that vector position. So normally I will try to draw out the scenario to help visualize the problem. So in this case here we have so if I draw my x, y and z axis. So on my x-axis 1, then -1, I have -0.2 nanocoulombs, and then -0.2 nanocoulombs, and then on my y-axis at 1, -1, I have 5 nanocoulombs, and then here I got -5 nanocoulombs. Then we asked to work out the electric field at the point 0, 0, 5, meaning that on unit 5 at the z-axis. Okay, so taking my first point, so it's difficult to draw out everything here in three-dimensional, so I'll just draw one just to give some idea how the vector looks like. Okay, so this is my position. So this is my vector pointing from my first charge to the position of observation. So if I call this my vector R1, this vector R1 is the position vector of our observation, which is 0, 0, 5, minus the position vector of the charge, which is this vector here. Okay, so my position vector, let's call this vector P. This is my observation point, and then Q1 I have a charge of -0.2 nanocoulombs, and then the position vector of that, I call it my R Q1, which is -1, 0, 0. Then I can work out my vector R1 will be equals to my vector P minus my R Q1. This will be 0, 0, 5 minus -1, 0, 0. This gives 1, 0, 5. So that will be my vector R1, and my unit vector R1 will be 105 divided by the magnitude, which is square root of 1 squared plus 5 squared will be square root of 26. And this gives us 0.196, 0.981. So that is for Q1. We can do the same for Q2, Q3, and Q4. So I define my Q2 as 0.2 nanocoulombs at the position vector RQ2, 1, 0, 0. And then my vector R be P minus RQ2, 0, 0, 5 minus 1, 0, 0. This gives me minus 1, 0, 5. The unit vector, so this should be R2. Unit vector will be minus 1, 0, 5 divided by square root 26. This gives me minus 0.196, 0.981. So for Q3, there will be minus 5 nanocoulombs. RQ3 is equals to 0, minus 1, 0. R3 is P minus RQ3 minus 0, minus 1, 0. This gives 0, 1, 5. And then the unit vector divided by square root 26. And then Q4, 5 nanocoulombs at position vector 0, 1, 0. R4, the vector between Q4 and the observation positions. 0, 0, 5 minus 0, 1, 0. Give 0, minus 1, 5. Unit vector R4 over root 26. And this gives 0, minus 0.196, 0.981. Here is 0, 0.196, 0.981. Okay, so that is all the vector positions between the charge and the observations. So next we can work out all the electric field one at a time due to all these different charges. The electric field due to charge Q1, coil E1, based on Coulomb's law, this will be equal to Q1 over 4 pi epsilon naught magnitude of our R1 squared times our unit vector R1. Q1 is minus 0.2 nanocoulombs over 4 pi. Epsilon naught is 8.854 times 10 to the minus 12. Magnitude of R1 is square root of 26. Square of that, there will be 26 times 10 to the minus 3. Or square root of 26, 3 squared, times our unit vector 0.1960, 0.981. And this should give us minus 0.014, 0, minus 0.068 volts per meter. E2 due to Q2 over 4 pi epsilon naught R2 magnitude squared times the unit vector R2. So I'm not going to rewrite all the values, but just going to quote the solutions. That will be equals to minus 0.014, 0, and 0.068 volts per meter. And then E3, there will be Q3 over 4 pi epsilon naught R3 magnitude squared times the unit vector R3. That should give us minus 0.339. Should be 0. 0 minus 0.339. This will be equal to minus 1.695 volts per meter. And then E4, because Q4 4 pi epsilon naught R4 squared unit vector R4, and that will give us 0 minus 0.339, 1.965 volts per meter. So this is the individual contribution of the electric field of each individual charge. So the total charge is just the vector sum of all this. Be E1 plus E2 plus E3 plus E4. Okay, so just do a vector addition of all this electric field, and you should get minus 0.027, then minus 0.678, and then 0 in the Z components, watts per meter. Putting a charge, I call it QP at position P of minus 2 nanocoulombs. The force on this charge, let's call it FP, will be equals to QP times the electric field at that position, which is our total E field. There will be minus 2 nano times or minus 0.027 minus 0.678, that will give us 5.423 times 10 minus 11, then 1.356 times 10 to the minus 10, and then 0 in the x component, newtons. The magnitude of this force will be the square root of the x component plus the y square root of the x component squared plus the y component squared, and that will give us 1.357 times 10 to the 9 is equals to 1.357 nanonewton. The unit vector of the force will be the vector divided by the magnitude of the force, and that should give us 0.04, 0.9990 Newton. So the direction, as you can see, is almost 0 in the x, almost 1 in the y. So mainly the force is almost purely in the y direction. Okay, so that's the solution for question 4.